All right, hopefully by now you know how to draw motion maps for scenarios that objects are moving a constant velocity for, so that we can go ahead and add in the idea of acceleration. We already know that motion maps use dots to represent the location of an object and arrows extending from those dots to represent the velocity. So something like that. Now we are going to represent acceleration too. Acceleration arrows are drawn above the dots to show the magnitude and direction of acceleration. Remember, acceleration is defined as the change in velocity over change in time. Because velocity is a vector, that means acceleration must also be a vector. So we're going to draw an arrow above that dot to show the acceleration of the object. Let's look at the first one. It says assume all objects start at the origin, and a car traveling east, originally going a speed of 10 meters per second, accelerates uniformly with plus 1 meter per second for every second for 5 seconds, or positive. So a few key things here. Traveling east tells me my direction of motion is positive. That means my velocity vectors should be pointing to the right. My initial velocity, or initial speed, is equal to 10 meters per second. My acceleration is equal to 1 meter per second, and it's in the positive direction as well. The time travel, or the time that we're looking at, is for 5 seconds. So let's start our object at the origin and traveling an initial velocity of 10 meters per second east, so we'll go to the right, and that size of arrow is going to be representing 10. Notice the acceleration is in the positive direction also, and has a value of 1 meter per second for every second that passes. So what that is telling us is that for every second that passes, the acceleration increases by 1 meter. For every 1 second that passes, the velocity increases by 1 meter per second. So if this is representing 10, I have an acceleration. This is the arrow I'm going to draw. I'm drawing it to the right because it's positive, a positive 1 meter per second, and it's going to represent the magnitude of 1. I know that's not quite scaled to the magnitude of 10 that is represented right here, but we can't draw everything to scale. If that happens, meaning that my acceleration of 1 meter per second for every second, after 1 second, I will no longer be going 10 meters per second. I will now be traveling 11. So my vector should be a little bit longer to represent that 11. The object is still accelerating, so you draw that acceleration arrow, and it's still an acceleration of positive 1 meters per second for every second. So the pink arrows would stay the same size. We have to continue this motion for 5 seconds. So far I have t equals 0 here, so this is 1 and 2. Then 3. Each time my velocity is getting larger. 4 and 5. Those acceleration arrows should be there to show that as well. The bottom portion, right below the motion map, asks you to talk about the direction of the velocity, the direction of the acceleration, and the resulting motion. So if we're looking at this one, the velocity is positive. It's east, which we consider positive. Acceleration is positive, which we saw by the plus sign. And to describe the motion, we see those velocity vectors getting larger, so it is speeding up. Let's look at another scenario below. A car traveling to the west, originally going 30 meters per second, accelerates uniformly by -5 meters per second for every second to evade the police car for 3 seconds. Starting at the origin, The idea here is it's traveling west. West to us means negative, so our velocity is negative. We have an initial velocity of 30 meters per second, and we have an acceleration of 5 meters per second, but specifically negative. So that means we will also be drawing our acceleration to the left to evade the police car for 3 seconds, so for a time period of 3. My initial velocity is 30, but west, so I'll draw it to the left, and that value should signify 30. If my acceleration is also to the left, my acceleration arrow has to be drawn to the left. That arrow, the pink arrow, will be representing 5 meters per second per second. So after 1 second passes, my velocity will have changed by 5 meters per second. Because it's in the same direction as my velocity, just like if you were to add two negative numbers together, that resulting product would be a larger negative number. So 30 meters per second to the left, and accelerating or changing at 5 meters per second to the left gives us a value of 35 meters per second to the left. Still accelerating, so that's still going to show an acceleration of negative 5 meters per second for every second. This has time equals 0, so 1 second, 2 seconds, and 3 seconds. I go off the page there. Now let's take a look at what our directions are in the resulting motion. The velocity is to the left or west, so that is negative. Acceleration is also negative, is seen by the negative sign up here. And the resulting motion is that the car is speeding up. Perhaps you shouldn't speed up to evade the police, but we can't all be so perfect. Why don't you pause, try the next one on your own, and then see how you do with it. Go ahead and pause now. Okay, after you tried that one, let's look at number 3. We'll go a little bit faster. A car originally going 20 meters per second accelerates uniformly by negative 5 meters per second for every second for 4 seconds to dodge the squirrel in the road. We're given an initial velocity of positive. This time it doesn't tell us east or west, but it does put a positive sign in front, and we know our initial velocity is 20 meters per second. The acceleration is just like the one before, negative 5 meters per second for every second, and you're traveling for 4 seconds. So we'll start, positive velocity has to be to the right, and negative acceleration has to be to the left. Just again like in math, if I have a positive number and a negative number and I'm adding them together, because this velocity is changing by this acceleration, or that magnitude, that would give us a smaller number after that occurs. Hopefully my arrow looks smaller there. You're still accelerating to the left while moving to the right, so my next arrow has to be even smaller. Same thing is happening, smaller. And so far we're at time equals 0, so that's 1, 2, 3. We need to go for 1 more second while still accelerating. If we were looking at this more closely, it's very conceptual with no numbers, but we should probably take a closer look and say, well, this would be 20 meters per second. If I accelerate with negative 5 meters per second after that 1 second, I would be down to 15 meters per second. I'm down another 5, so this would go down to 10. This would go down to 5, and this one should actually be down to 0 meters per second. So at that point, you should have gotten to a dot. Qualitatively, we're looking at it, it's not the biggest deal, but if you're starting to use this with real numbers to find out the velocities at certain positions, you do want to be careful with that. Looking at the velocity here, we have a positive velocity, the direction of velocity, we have a negative acceleration, and the resulting motion was going from 20 to 0, which is slowing down. So hopefully you're kind of picking up the idea that this direction of acceleration matters, and that objects that accelerate don't necessarily speed up. That's a common misconception amongst the way people use acceleration. People will say accelerate or decelerate, but really the term acceleration just means changing velocity. It doesn't mean speeding up or slowing down. So try to take deceleration out of your vocab. You can flip to the back side and continue on. And then on the bottom, there's actually a portion that says trends and conclusions. So really let's look at here for this. You can check out the answers on the site for the rest of them. But the trends and conclusions are looking at these velocity and acceleration directions along with the resulting motion, you can find a pattern. If your velocity is in the same direction as your acceleration, so this would be one example, something traveling to the right and accelerating to the right or in the positive direction, or something traveling to the left and accelerating to the left, the object will be speeding up. The flip side tells us that if I have an object traveling in the positive direction but accelerating in the negative direction, or an object traveling in the negative direction and accelerating in the positive direction, so therefore my direction of acceleration and direction of speed or velocity are opposite, the object will be slowing down. So, to summarize, acceleration and velocity are in opposite directions. You get slowing down. If acceleration and velocity are in the same direction, you see the resulting motion of speeding up. So even with a negative acceleration, you can be speeding up. Even with a positive acceleration, you can be slowing down. I hope that clarifies the fact of acceleration being a vector and the fact that you can have objects accelerating that are slowing down or speeding up. We'll talk about a third scenario where you will see acceleration later. All right, goodbye.